Hello, 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 everybody. Unit 5, Lesson 3, we are going to be evaluating independence today. And I'm not talking about July 4th, the Declaration of Independence and Independence Day. I am talking about probability and independence. And on the test, as of now, at this point, there always seems to be 2 questions or so, more than one, like 2 or maybe even 3 that having to deal with some sort of independence. Okay, when it comes to probability. And I will discuss what this is right here on the board in a little bit. But for right now, let's move forward. Okay. Now, independent events. We say that 2 events, let's call them A and B, all right? 2 separate events, A and B, are independent of each other if the following is true, okay? Highlight. All right. So if I take the probability of B given A, and that's equal to the probability of B, all right, then they're independent, all right? Or you can say, likewise, the same thing would be true. The probability of A given B equals the probability of A. All right. I'd like you to just see one thing that's overly obvious right now. Whatever is listed first in your given statement is the one it's going to be equal to individually. Okay? Notice the probability of B given A equals the probability of B. Likewise, when I switch that, if I say the probability of A given B, weird. Wow. All right? Probability of A given B, that should equal the probability of A. So whatever is listed first, that's what it's going to equal to its solo by itself. So what does that mean? That means if, and I'm going to use a little bit of notation here, if the probability, I'm going to use this first one, of B given A is the same as just the probability of B, all right, then A, the probability of A, really, it doesn't matter. All right? If A doesn't affect B, then B is independent of A. A has no effect on B because if you take B with respect to A, and if you take B alone and they're the same, right, then A, it doesn't matter. Okay? So they're independent of each other. That's what independence means when it comes to probability. All right? Now, let me reiterate, and I've said this before, that bar, okay, this straight bar here that is here and here, that means given, okay? And we've gone over given with conditional probabilities, okay, on last lesson, okay? A given B or B given A. All right, so we're gonna have to know how to do that as well, and we're just gonna build off that. Okay, that's called scaffolding in teaching. When you are learning something new using something you already know, or scaffolding that. Yeah, you know, that's your little irrelevant fact for the day. So let's start to apply this, shall we? Let's start to apply this right now. Example 1 says, a survey, and that's supposed to say of, not or, of 57 sixth graders. Now that little crosshair thing's in the way. Oh, okay, let's start over again. Let's refocus, Visca. It's okay. It's fine. Example 1 says, a survey of 57 sixth graders was done to determine which subject was their favorite. Dang right math is on there. The results are shown in the table below, sorted by gender. All right, so let's just take a look at what we got. Here are all the males in blue. Boom, total of 27. And I just Here are all the females. Okay, the total is 30. All right, if I add 30 and 27, I get 57 total. That's how many people were asked about their favorite subject. And now, here are all the math. 5 girls, 10 boys. It's a total of 18. Here is the English. 6 female, 4 male. That's a total of 10. Social studies, 10 female, 9 male. It's a total of 19. I don't know how I set it up, so social studies was more than math, but we'll just fly with that for now. And last but not least, we have science in the mix. Wow, I thought I did blue. Science in the mix. That is 6 females and 4, what? 6 females and 4 males. That should say 10 here. Wow, look at me catch this. All right, now here's the interesting thing. If I add these this way, yes, that should say 10, because 10 and 10 is 20, 38, 48, 57. That should be a 10, not a 9. Interesting. I love catching typos. So I guess that could be a calculation thing, but hey, let's move past it. Now we understand our table. Okay, so I'm going to erase all this, but I'm going to put a 10 right in that spot right there. All right, so this should be 10. Okay, now, based on this data, I'm looking at part A. Based on this data, are the events the student is male and math is a favorite subject, are they independent of each other? So I'm going to use, oh boy, I'm going to use capital M for male, and I'm going to use lowercase ma for math. Okay, you know what? I can use A for arithmetic. How about that? A is for arithmetic or math. So if for them to be independent, let's go back here. All right, the probability of one given the other has to equal the probability of the first one. Okay, so let's bring that into play here. The probability that I pick a student that is male, given that I'm only choosing arithmetic or math, is that equal to the probability of just a male? Remember, whatever goes here is the first one here. So we need to figure both of those probabilities out. If they are equal, then those two probabilities are independent. If they are not equal, then those two probabilities are not independent. All right? So let's go ahead and try this out. Now, first of all, the probability of males. Okay, I get my blue highlighter. How many males do I have? I go 27. 27 out of a total 57. So this is 27 out of 57. Okay, if I reduce that, I'll put this right here, equals. I can reduce that, oh my God, 19. 3 goes into both of those. 9 over 19. That's what 27 over 57 reduces to. So now, let's figure out what the probability of a male given math or arithmetic. All right, let's use yellow. Okay, I am given just math to pick from. All right, out of a total of, okay, we have 18 math. How many of those are male in just my math column? 10. 10 out of 18. If I reduce this, ooh, that is 2, yeah, I'll be okay. That is 5/9. Those are not equal, so they are not independent of each other. And that's it. I'm just finding those two probabilities. Let me reiterate this one more time. I am finding the probability of given, which happens to be 10 over 18. Wow, that went right over the yellow, which reduces to 5 over 9. Then I am taking the probability of just the males, because remember, that's the first one, right? 27 over 57, that reduces to 9 over 19. They are not equal, so they are not independent. If they would have been equal, they would have been independent. Okay? Not too bad. Let's take a look at the second one, which is B. And I really can't scroll down anymore. I'm going to lose the table. And B says, does this data suggest that gender and a preference for social studies are independent of each other? So let me erase all this. I got to put my 10 back for science, but we really don't even use science here. So 10, 10. All right. Now, social studies, which if I do this right, yep, that's the column right there. Here's social studies. All right. This column right here. Now, we need to suggest that gender, male or female, okay? So this is what I'm going to do. So the probability that someone selects social studies as their favorite, if they're male, does that equal the probability of social studies, okay? And let's not forget, we'll try the other one too, the probability that someone would select social studies as their favorite subject given they're female. If they're independent, that should also equal the probability of the first one, which is social studies. Because it says, does this suggest that gender? It doesn't say male or female, so I'm going to try them both. All right? So let's start referencing our table, and we will start. There we go. We need our table back. Social studies and male. So I'm going to look at this one first. The probability that I pick social studies given that I'm a male. Here are all the males that I'm given to pick from, and social studies is already in blue. Where do they intersect? 9 males out of the 27 I've given to pick from prefer social studies. Okay, so that ratio is 9 to 27, which also reduces to 1/3. Now, what's the probability of just social studies? All right, let's go back up to our table. My social studies column is right here. Well, there are a total of 19 social studies. Out of how many in our total survey? Well, out of our 57 total, 19 of them pick social studies, right? That's just the probability of social studies, 19 over 57. Guess what? 19 goes into 57 3 times. They are equal, so they are independent. All right, they are equal, so they are independent. All right, let's try the next one. And I'll be honest with you, we already have half the work done. I just figured out the probability of social studies, didn't I? It was 19 over 57, which ended up being 1/3. Are they equal? Let's see. So let's pick, all right? Let's figure out our probability, our fraction of all those that like social studies given just females. So let's go back up here. Let's go. We are given just females. This is what we're given. So we are given a total of 30. All right. So how many people, how many of these girls pick social studies? So where do they intersect? Right here. 10 out of my 30. 10 girls out of my 30 girls picked social studies. 10 out of 30. And guess what? That absolutely reduces to 1/3. These two probabilities are also independent. If they are the same, they are independent. If they are not the same, like an A, then they are not independent. All right, so there is a second way to find independence. They refer to it as the product rule for independence, but let's just do it because that is always easier to understand things when we're doing things. So here we go. Well, remember, it's easy to find given. Part of finding independence is we need to know some probability of something given is equal to the first right here. This is given. Well, given, okay, conditional probability of A given B is real easy to do in a table. But remember, I think it was last lesson, sometimes we can't find something given something else. If we don't have a table, it's not that easy. There's also an algebraic way to do it. And this is the algebraic way to do that, right? I can take the probability of A and B and put it all over the probability of B. So that's ultimately going to lead us to another, that will ultimately lead us to another way to find independence. So how do we find independence right now? Right now, the probability of A given B has to equal the first one, the probability of just A, right? But look it, in for this, if I don't have a table to do this the easy way, I've got to do this the algebraic way. Like if they just gave me numbers for these, okay? So I'm going to substitute that in for my given here. If I need to find the probability of A given B, and I don't have a table, I have to do it this way. So I'm literally going to substitute that in. I've got the probability of A and B, okay, all over the probability of B. That was the other way we found condition or given. And that's still going to equal the probability of A, right? Now, what happens if I want to get rid of that fraction? Algebraically speaking, if I want to get rid of the denominator on the left-hand side, when I multiply this by the probability of B, and what I do to one side, don't I have to do to the other? That gives us the following formula. If I take the probability of A and multiply it times the probability of B, it should equal the probability of A and B. If this happens, that also proves independence. This is an easier way to prove independence. All right, this right here is another formula to prove independence. No, I don't want crayons, silly. This one, this equation right here. If I multiply two individual probabilities together, and it's the same as the probability of those two, like one and the other, okay? And they're equal. If they are equal, they are independent. If those two expressions are not equal, then they are not independent. Now, what do I tell my students? All right, if you are given the given right here, if they give you to use, I'll use this one, it's cleaner. All right, if they give you the given, yep, look at me go. If they give you the given in the word problem, then use this one. Use this whole thing. If they don't, then chances are you're going to have to use this thing right here that I've highlighted in yellow. All right? So let's take a look at how that works. We have a word problem here. Okay? Let me erase some of this. The probability that a person is left-handed is 12%. The probability that they have brown eyes is 42%. And the probability that they have brown eyes and are left-handed is 2%. Is the event of having brown eyes independent of being left-handed? Support your answer. All right. The probability of being left-handed is 12%, 0.12. The probability of having brown eyes is 42%. The probability of having brown eyes is 0.42%. The probability that they have brown eyes and are left-handed is 2%. So the probability of having brown eyes and are left-handed is 2% or 0.02. So let's see if these things are equal based on our equation here. Okay, if the probability of left-handed times the probability of brown eyes equals the probability of left-handed and brown eyes, all right? I mean, I don't think it matters which letter I put first here, but in order to stay consistent with what I've written here, I'll rearrange them, all right? So is 0.12 for left-handed times 0.42 for brown eyes equal 0.02. I don't know, let's take 0.12 and multiply it times 0.42. We have a calculator. Oh, let's clear that stuff out. That's calculus. 0.12 times 0.42. That is 0.0504. Let's cut that off 2 decimal places. That is 0.05, and I could say 04. Does not equal 0.02. So what does that mean? That means they are not independent. Quite simple, all right? If one thing equals the other, then they are independent. If they are not equal, they are not independent. All right, let's get in a little bit of practice here. Example 1. You are asked to determine if the 2 events, a randomly selected student has asthma and a randomly selected student has a household member who smokes, are independent. Show this using both conditional probability and the product rule. All right. Well, let's go. We have this table in front of us here. And the 2 things, let's first do conditional probability. All right. That means the probability student has asthma, I'll call that A, given, that's the condition, that they live with a household member who smokes. Does that equal the first one, the probability of having asthma? Are they independent of each other? Let's use this table and find out. All right? So, first thing I want to do is this one right here. All right? The probability that someone has asthma given they live with a household member who smokes. Here we go. At least one household member smokes. Right here. All right? That means out of my 395 people that live with someone who smokes, I am choosing the asthma just out of that given. Okay? Here are the students that have asthma. Where's the intersection? Right here. This means 113 out of my 395. Okay? That is a probability that if I choose someone, they have asthma given they live with someone who smokes. Now, what's the probability, all right, that just point blank someone has asthma? All right? So, let's go here again. Highlighter. These highlighters come in crazy good. Here's asthma. Here's the total number of people that have asthma. And this is the total of people that were interviewed. So that is 182 out of 937. I got to see if those are equal. They do not look equal to me. But just to be sure, let's try this out in the calculator. All right, turn this on. And I have 113 divided by 395. And let's call that 0.29 or 0.286. Let's go one more decimal out. Okay, and then I have 182 divided by 937, and that is 0.194. Those are definitely not equal. All right, so 0.286 does not equal 0.194. So they are not independent of each other. Boom. Okay, I'm going to get this out of here now. Cut. And they want us to do both ways to prove this. So now I've got to use the product rule place. That means the probability of asthma, my two events, I multiply them in terms of probability living with someone that smokes equals the probability of them both, asthma and smokes. All right? So let's look at our table and get this information. Now, these are both going to give us the same response. Both of them should not be independent. We just figured that out right now. So this should also give us a not independent response. All right. Here we go. The probability that someone has asthma. Where are the asthma people? Right here. That is 182 out of 937. We just did that. That is 182 out of 937. I'm going to multiply that, right, by the probability that someone lives with a household member who smokes. 395 people out of the 937. 395 out of the 937 equals, move this over here, the probability that they have asthma and they smoke. Okay, so let's look at our table and find that out. Highlighter, asthma, smoke, okay? 113 do both. 113 live with someone who smokes and has asthma out of my 937. All right? So I've got 113 out of 937. I need to see if those two are equal. And you know what? Everything being the same, I think you can just cross off the bottom. But let's get decimals. Why not? We have a calculator. Let's go here and let's check it out. Clear this. No, there you go. We've got parenthesis 182 divided by 937. I need a division sign. Times 395 divided by, 937. A lot of mistakes to be made. Always when you're going fast, you got to look up in the calculator and always make sure that's right. That should be 0.082, let's call that. 0.082. Now, I know for a fact these two aren't going to be equal because we already did this. If I get 0.082, I'm going to have an issue here. All right? We already did 113 out of 937. That was 0.194. They are not equal. So they are also not independent. And we knew that. We already did this. We were just showing you that both ways give you the same results. All right? Good. Good. All right, this will be our last one, example 2. The results of a poll of 200 students are shown in the table below. Preferred music style and gender, okay? For this group of students, do these data, that always sounds weird. Does this data suggest, I would say, but whatever. Do these data, because data is the plural of data, suggest that gender and preferred music styles are independent of each other? Justify your answer. Let's pick one gender and one music style, okay? I'm going to go with, I get some choice here. I'm going to go with males, because I'm a male. And let's go with, rap is too easy. Let's go with techno. Math, Visca. Man, I'm good. I've got so many talents. I'm untapped talent right here. Anyways, are those independent of each other? All right, well, let's figure it out. All right. Now, they said there was a total of 200 people. So if I do this, and if I do this, the total will be 200. All right. So if I add all these down, I mean, I don't even know. I'm going to add my techno column, and that should give me 90. I'm going to add my rap column, and that should give me 65. And I'm going to add my country column, and that should give me 45. And if I add those three together, it definitely gives me 200. All right. Now let's do males and females here. All right. So the males have 30, 70, 80, 94, which means females should be 106. Let's see what that is. That's 50, 60, 70, 80, 90, 102, 106. Absolutely. All right. So now that we have our totals, we're going to say, and we could pick either way. We can do the product way, but when we have a table, I like to do the given way. So the probability that someone likes techno, given they're a male, does that equal the probability of the first one, of just techno? Are they independent of each other? Let's see. Sorry, I got carried away. Now, let's do the first one here. Techno, given male. So out of all the males I've got 94 males to pick from. Where's the techno here? This is 36 out of 94. Does that equal the probability of just techno? All right, well, if I look at techno, there are a total of 90 people out of the 200 that liked techno. Okay, that was their preferred music. Let's put those in the calculator and see if they're the same or not. 36, I should probably move this right here, divided by 94, and that gives me 0.38. Well, I know for a fact that's not what 90 over 200 is going to be. It should be, I think, 0.45, but let's do it anyways. 90 divided by 200, 0.45. So, badoosh, move this thing out of the way here. All right, we get 0.0. Yeah, I'll be okay. That's the previous one. 0.383 does not equal 0.45. So guess what? They are not independent. You've done good, kids, because we're done. We went 2 minutes over my 30-minute mark. But you know what? Stats and probability are fun. Yeah, I said it. It's fun. Not fun like calculus is fun, but it is fun because we get to do things like, you know, males, females, and techno. Dance, techno, math. Yeah, save that one. In fact, download this, rip that audio, and make that your ringtone. See you later. We only have one more lesson. Oh my goodness, for the year. We're not going to do Unit 5, Lesson 4. We're not going to do Unit 5, Lesson 5. We're going to jump right to Unit 5, Lesson 6. And that's going to be the last lesson for the year. And then we review for the final, which I don't think I'm going to put up too many videos for that. I might do some answers to some of the old regents up there. But you know what? I've enjoyed the ride this year, and I hope you have too. So I will see you. I promised myself I wouldn't cry. I will see you for our last video when I do it, maybe in a couple of days. And for you, that might just be a couple of moments, a couple of seconds, because you might be listening to this, and I have already done that last lesson, which means you're like a time lord. Weird. Freaky. If you are, can you please go back and give me the numbers on the jackpot to that Mega Millions with 750 million and no one won it? Because I could use those numbers. I will. Come on, I'll give you $10. I'll give you $10. Yeah, get out of here, crazy kid. I'll see you for our last lesson. See ya.